Somewhere in NASA's planning documents is a rough date sometime in the next decade. A human footprint could press into the red dust of Mars for the first time. Some scientists go further, suggesting permanent colonies could exist there by 2050. That means someone alive right now, maybe even watching this, could end up being one of the first people to call another planet home. I'm James Vince, and you're watching Astrum Orgin. Today we're looking past the excitement of getting to Mars and asking a harder question: once you land, what is actually waiting for you there? What kind of weather, terrain, and hidden dangers would a future Martian settler have to survive? A trip to Mars takes roughly 3 months with a good launch window. That sounds manageable, like a long cruise, except for one detail: you'd spend that entire stretch outside Earth's magnetic field, soaking up solar radiation and cosmic rays. Long-term exposure like that raises real risks of cancer and neurological damage. Engineers are testing fixes such as lining spacecraft walls with water, since hydrogen is unusually good at blocking radiation, though none of these solutions are fully proven yet. Once you arrive, Mars isn't as alien as you might expect. A Martian day lasts 24 hours and 39 minutes, barely longer than ours. Its year stretches to almost 687 Earth days, which makes sense given how much further out its orbit sits. Mars even leans on its axis at a similar angle to Earth, about 25 degrees compared to our 23.5, which means it experiences real seasons, complete with summer and winter. Those seasons swing hard, though. Temperatures can plunge to around -43 degrees Celsius at the winter poles and climb to roughly 35 degrees near the equator in summer. During each pole's winter, it sits in total darkness, just like our own polar regions, except the cold there is so extreme that carbon dioxide in the atmosphere actually freezes solid, forming slabs of dry ice that pile onto polar caps made mostly of water ice underneath. Time-lapse images from orbit even reveal strange spiral patterns carved into that ice, believed to be shaped by the planet's rotation through something called the Coriolis effect. That frozen carbon dioxide doesn't stay frozen forever. As it warms and turns back into gas, it triggers strong winds, and that sets the stage for the most dangerous weather Mars has to offer: dust storms so massive they can swallow the entire planet. From a photo, Mars can look like a place of complete stillness, just rust-colored plains and scattered rock. But roughly every 3 Martian years, or about 5.5 Earth years, that stillness breaks. A regional storm grows, merges with others, and eventually engulfs the whole globe in choking dust for weeks or even months at a time. Here's the twist: Mars wasn't always like this. Billions of years ago it had a much thicker atmosphere and possibly flowing water. As that atmosphere thinned to less than 1% of Earth's, the planet lost its ability to hold onto heat. Stand on the Martian equator at midday and your feet might feel 23 degrees Celsius while your head sits at freezing. That wild temperature gap between ground and air drives constant wind. Dust gets airborne 2 main ways. Sometimes towering dust devils, some over 8 kilometers tall, spin up when sunlight heats the ground and forces warm air to rise rapidly. But most Martian dust lifts through something called saltation. Heavier sand grains get pushed by wind, crash back down, and knock smaller dust particles loose in the process. Once airborne, Martian dust can stay suspended for months because gravity there is so much weaker than on Earth. And because dust absorbs heat from sunlight better than the thin air around it, it starts warming the atmosphere itself, pulling in more wind, lifting more dust, and snowballing into a storm. These storms aren't as physically violent as movies suggest. Top wind speeds hit around 97 kilometers per hour, but Mars's atmosphere is so thin that even fast wind barely pushes on anything solid. A single gust there carries a fraction of the force it would on Earth, which is why science fiction scenes of storms toppling spacecraft or ripping satellite dishes off their mounts don't really hold up. The real killer is darkness, not force. Scientists track how much sunlight makes it through Mars's atmosphere using a measurement called aerosol optical depth. On a normal day, that number sits around 0.5. During a full planet-wide storm, it can spike to somewhere between 9 and 11, representing a near-total blackout of sunlight. For context, the thick smoke from a major wildfire on Earth that turns day into night only reaches about 7 on that same scale. In 2007, NASA's Opportunity rover was perched at the edge of Victoria Crater when the largest dust storm it had ever seen rolled in, cutting sunlight by 96%. Its solar power output collapsed from around 700 watts on a clear day to just 128 watts, dangerously close to the 150-watt threshold where batteries begin draining faster than they can recharge. Mission controllers scaled back operations drastically, limiting communication to once every 3 days, and waited nearly 2 months for the skies to clear enough for Opportunity to keep moving. Spirit, its twin rover, wasn't as fortunate. After years of exploring, it became permanently stuck in soft, sulfate-rich soil in 2009. Unable to reposition itself toward the sun, its power output kept dropping through repeated dust storms until it could no longer run its internal heaters. Sometime in 2010, Spirit likely suffered a fatal power failure in the freezing Martian night and never responded again. Opportunity itself eventually met the same fate. In 2018, a planet-wide storm buried its solar panels in dust so thick that scientists measured near-total sunlight blockage. Without power for its heaters, the extreme temperature swings destroyed something critical inside the rover, ending a mission that had lasted 15 years past its planned lifespan. Learning from those losses, NASA has been testing very different kinds of explorers. Ingenuity, the first helicopter ever flown on another planet, was originally built for just 5 short test flights. It ended up completing 72 flights over almost 3 years, traveling more than 17 kilometers before a hard landing on featureless sand ripples damaged its rotor blades in January 2024, grounding it for good. Even in retirement, engineers call its data invaluable for designing future Mars aircraft. Boston Dynamics' walking robot, Spot, represents another approach. Unlike wheeled rovers that can get permanently trapped in soft sand, Spot can climb stairs, cross rubble, and right itself after a fall. Working with NASA's Jet Propulsion Laboratory, teams of Spot robots have already mapped cave-like terrain on Earth completely on their own, without any human steering, practice for a future where they might explore lava tubes and caves on Mars, places that could shelter future colonists from both radiation and these punishing storms. Even the soil holds problems and possibilities. Experiments simulating Martian regolith have successfully grown crops like tomatoes and spinach, though the soil contains toxic perchlorate salts that need to be rinsed out before farming. Ironically, those same perchlorates can pull water from the air and release oxygen, both useful resources for survival. NASA's Perseverance rover even tested a device called MOXIE, which successfully proved that oxygen can be extracted directly from the Martian atmosphere's carbon dioxide, an early but promising step toward astronauts producing breathable air on-site rather than shipping it from Earth. None of this means Mars is unlivable, it just means location matters enormously. Sites near the poles offer easy access to water ice, while deep craters like Korolev hold frozen reserves that could be mined for drinking water and oxygen. Regions closer to the equator get more consistent sunlight for solar power but come with harsher storm exposure, which is why many mission planners lean toward hybrid locations that balance both. Lava tubes remain one of the most promising options of all, natural underground tunnels left behind by ancient volcanic activity, wide enough in some cases to fit entire buildings, offering built-in protection from radiation, temperature swings, and the worst of the dust without needing much construction at all. Beyond the science, there's the matter of simply enduring life there. Confined spaces, limited company, and complete isolation for months during dust storms would place enormous psychological strain on any crew, especially knowing that unlike scientists in Antarctica, there's no easy way home if things go wrong. Add in the physical toll of lower gravity, weaker bones, poor circulation, and vision changes already observed in astronauts who've spent long stretches on the International Space Station, and it becomes clear that Mars won't just test our engineering. It will test human endurance itself. There's also the matter of distance. Even a simple message to Earth can take anywhere from 3 to 22 minutes to arrive one way, meaning a round-trip conversation has a minimum 6-minute lag. During an emergency, especially one caused by a storm cutting off communication entirely, colonists would have no choice but to solve problems entirely on their own, with no real-time guidance from mission control back home. So the dust will keep swirling, the temperatures will keep swinging widely between day and night, and somewhere out there, the technology needed to finally live with all of it is slowly taking shape.